later on. One thing that's been known for quite some time is that if you have a hot piece of metal, it'll start to glow. And eventually, you can make it glows white hot. When something is glowing white hot, do you know what colors of the rainbow it's emitting? All of them. Yeah. And so if I take a metal, this is stainless steel, but if I take a metal spatula like this, it'll just start heating it up. Hopefully there's no chemicals. But it'll start to glow. Right now it's not really glowing, but it's radiating electromagnetic radiation, which we call. And the electromagnetic radiation is infrared. I can feel it. I can't see the infrared, but I can certainly feel the electromagnetic waves hitting my hand. When the electromagnetic waves of infrared hit my hand, what do they do to my hand? Do you know what they do? They transfer energy. Electromagnetic radiation's transfer of energy. And what does infrared do specifically? Do you know what infrared does to matter? Yeah, and so it causes vibrations. If those vibrations get too extreme, it could do something called denature proteins. Proteins rely on having all the atoms in the right places. And if they're out of place, then you can get some damage. And that would be a burn. Can you see it starting to glow? The color? It's starting to glow. That's taking it from the infrared into the visible. And so after infrared comes what color? So it's a little higher than infrared. A little higher than infrared is visible light, and the first color that's going to come after infrared is red. And so this is going to start glowing red hot. This light I want to turn off. The switch is back there. Can you see the red? And then eventually it's going to start to glow yellow, and then orange, and then eventually white hot. I'm not going to get this white hot. I'll just get it red hot right now. So this is a red hot piece of metal. And I can feel the infrared. I can see the red. I can't feel the red because the red is just exciting electrons in my eyes. And we can see it. So, in order to get this white hot, we've got to make sure this stuff doesn't melt. And this is already looking damaged. So. And so we have light bulbs. Let's take a look at the basic construction of a light bulb. And what does visible light do? I did an exam yesterday. It's probably chemistry, a low priority right now. But what did it do? Visible? Like radio waves. What do radio waves do?
Excites the electrons.
In everything or in metals? And then we had microwaves. What do microwaves do?
They ionize
They ionize metals, yeah, but they also
make it so the electrons can break off.
Yeah. And so if you have an antenna here, say, and you have radio waves coming, then what happens is the electrons can start to oscillate with the radio waves, that is, oscillate up and down. This will create a signal here. Now, this is for radio waves. If you go to microwaves, microwaves are higher energy, light. Higher energy light will have a shorter wavelength or a longer wavelength. Higher energy light. Well, probably you'll just have to go back through and take a look at that, I think, is the thing. The higher energy light has a, I mean, if you were to guess, what would you guess?
Shorter wavelength?
Shorter wavelength, is correct. And so higher energy light has a shorter wavelength, which is going to increase or decrease the frequency of oscillation of electrons.
Increase the frequency?
Yeah. And so there are certain things that we need to cover. These things are, and this is just lambda. Lambda is the so it's easy to forget. Like I said, it's the percentage of memory that you lose is very, especially when you're cramming your memory with other stuff, like this stuff for the test. But the problem is that this sets up like a cascade effect where it becomes very difficult to catch up. And so, even though we just have the test, you still want to try to stay on top of the material. Otherwise, it becomes a horrendous task when the exam comes for studying, because you have to go back and review everything. But lambda is the wavelength, nu is the frequency. So we call this lambda, Lambda. This is called nu, N-U, nu. These are the Greek, lowercase Greek symbols for that. Lambda and nu are very, very common. So the frequency, we have one more thing, and let's see. The frequency depends on how fast this comes, but all light comes at the same speed. C is called the speed of light. And so this is all reviewed here, I think. And so if it's coming at the speed of light, which is like 186,000 miles an hour, something insanely fast, this electron is going to be oscillating very fast, unless the wavelength is very long. In radio waves, the wavelength is long, meters or even kilometers long. But for visible light, the wavelength is extremely short. And so this is oscillating. The frequencies vary quite a bit. But the higher energy light is going to cause this to oscillate, and if it oscillates too much, it'll ionize. That is, it'll get knocked off the matter because the vibrations are too much. And they aren't really electron vibrations, they're electron movement. The vibrations are from infrared. Vibrations, when we talk about vibrations, we're looking at molecules. And so if we shine infrared light at this metal, it's going to get very hot because not only do the electrons get excited, but also the atoms start to move as well. And so microwaves, they have enough energy to actually knock electrons off this. But for heavier things like a water molecule, what microwaves can do is, you shine the same light at water. You do this in a microwave oven. You shine this microwave radiation at this. It's not going to ionize the water. What happens is the water has a negative end, which we call delta minus, and a positive end, which we call delta plus. And so this is going to flip around in the field as well. There are certain rotations that are allowed for water, just like there's certain vibrations that are allowed for water. And so microwaves will rotate the water molecules. So light interacts with matter. And so what we can do is we can do this. In a light bulb, we'll take a tungsten filament and then excite the electrons in the tungsten filament. But we're not going to excite it with light. we get excited with light. Instead, we're going to excite it with electricity. And so what's going to what's going to happen is the electrons are going to start flowing through the wire. And as electrons flow through the wire, they meet some resistance. It's not perfect flow of electrons through there. There's some resistance as electrons have to move through the lattice structure of the metal. And there are vibrations and other things that might interfere with how electrons move. And so what that does is it causes this to heat up. And so eventually this will glow infrared hot, and then it'll go red hot, and then yellow hot, and orange hot. And eventually, if we get it hot enough, it will glow white hot. The thing is, we don't want the metal to melt, and so you have to use a high melting point metal. And tungsten's good because it has a very high melting point. But the problem with tungsten is it's easy to oxidize. So if you have a hot piece of metal, that stainless was starting to oxidize. Stainless is very resistant to oxidation. But tungsten has a symbol W. And so what we have to do is we have to have it in an inert atmosphere. And so inert just means it won't react with the tungsten. If air, that is, if oxygen gets in here, then forget it. The tungsten is going to oxidize. And when it oxidizes, it forms a tungsten oxide, which doesn't conduct electricity, and it's very brittle. So this thing just falls apart, basically. All right, so what we're going to do is this is going to emit infrared. Infrared has long wavelengths, but not all the electrons have the same energy. Then this is going to emit red, which has a shorter wavelength, and then orange, which has an even shorter wavelength. And then what comes after orange?
Yellow.
Yellow, which has a shorter, after yellow?
Green.
Green. What else?
Blue.
Blue.
Indigo.
Indigo.
Violet.
Violet. Once we get all the colors of the rainbow here, that's going to appear to our eyes as white light because of how the colors mix. And so we end up with white light. After violet comes what? Ultraviolet. We don't want much ultraviolet light from this. You have to watch out because some light bulbs will emit ultraviolet. It's going to be potentially damaging to you because ultraviolet does what? Yeah, damage your skin by? What does ultraviolet do to matter? Breaks bonds. It breaks bonds. Well, you don't want bonds like your bonds in your DNA to be broken by ultraviolet light. Some people are saying that even violet light, indigo light, and blue light can damage your eyes because those are a little bit too high in energy. So those colors of light are emitted from screens, like computer screens. So some people actually wear blue blocker, things that filter out the higher energy visible light to protect. You have blue blocker on your glasses? Just to prevent damage to your eyes. They're saying it's a little bit too high in energy. Oh yeah, right. It's also definitely important for that. Okay, so hopefully there's not much UV, and hopefully there's not much. What comes after UV? X-rays. When I was working with X-rays, we generated using copper filament, getting the electrons very excited in that copper filament, and then that would emit X-rays. But in the standard light bulb, you aren't going to worry. It's not going to get that high enough in energy. And maybe marginal amounts of UV energy. In fact, we call this the spectrum of the light bulb. You have different spectra. Spectrum is singular, spectra is plural. So there's something called the solar spectrum, which I'd like to bring up, but this is dead. I don't know. On the solar spectrum, there's going to be some infrared. There's probably some radio as well there. But it's going to peak in the visible, and then there's going to be some UV here. And so if we look at this as Roy G bid, and then look at this as the intensity, actually there should be a little bit more. We look on the y-axis as the intensity. The intensity is just the brightness of it. And so we see a pretty even distribution of the colors of the rainbow you'd expect from the sun. However, in certain light bulbs, some light bulbs appear more red. Some light bulbs appear more blue, depending on the spectrum. And so, as far as light bulbs go, they're more, the light bulbs that emit more red light are going to appear, softer here. And then you have light bulbs that emit more of the higher, these are going to appear whiter or hotter. And so we have different spectra from the light bulbs, which gives it a slightly different color to it, the white or more towards the lower energy colors here. And so the red is lower energy, the violet is higher energy visible light. The colors of things come from this. Some things appear white. Some things appear white. The things that appear white don't absorb any of the colors of the rainbow. And then there are some things that appear black. Black objects do what? They absorb all the colors of the rainbow. And so if you absorb all the colors of the rainbow, then it looks black. If you transmit or reflect all the colors of the rainbow, it's going to be white or maybe a mirrored type thing. Now, if you look at plants rely on photosynthesis for their energy. That is sunlight. And so plants, what color of the rainbow do leaves, green leaves, absorb?
Everything besides green.
Okay, one thing is it can absorb everything except for green. If it absorbs everything except for green, then only green light passes through. But why would it absorb everything other than green? Why not absorb green too? The leaves really, to make full advantage of the solar spectrum, should absorb all colors.
Has something to do with the chloroplast?
Yeah, it has something to do with that, and also it has something to do with, if something absorbs all the colors, how is it absorbing all the colors? And so when we look at how the plants absorb, the plants would be more effectively served by absorbing a single color because of the energies. It takes a certain amount of energy to do for an excited electron to appear. And a certain amount of energy to excite the electron to cause something to happen. And so what plants will do then is they can have a single absorbance or multiple absorbance. So when we look at how things absorb, we look at the color wheel. Let's say the color wheel. What do you think the brightest part of the solar spectrum is? It's not totally even here, but one of the brightest parts of the solar spectrum is the lower energy or the higher energy color. The lower energy, actually, the red, orange, infrared red, orange. And so if plants absorb in the lower energy, that is because it has, let's say here, it has more intensity here in the red. And if it has more intensity in the red, then this would be the most intense part of the solar spectrum, and therefore you could want to absorb that. And so what we see for plants is a different way of generating the color green. And that has to do with the complementary colors here. So if it takes out red here and absorbs the red, do you know what all these other colors add up to? And so if we remove red, all these other colors add up to green. And so something that appears green could have all the colors except for green absorbed, or it could remove its complementary color red. And that means the remaining colors add up to green. Let's say if something absorbs yellow. If something absorbs yellow, do you know what all the other colors add up to? Yeah, violet. So if something absorbs in the yellow, then it should appear violet according to the color wheel. Likewise, if something absorbs green, do you know what color it's going to appear to your eyes?
Red.
Red. And so there are different ways that we can make color. One is we can absorb all the colors except for the color that you see. Two, we can absorb one color and then see what the other colors add up to. Three, we can absorb multiple colors and then see what those colors add up to. And so an example of that would be like an LED TV. You know, the LED TV only has 3 colors. You know what the 3 colors are?
Red, green, blue.
Yeah, red, green, and blue. But it turns out with red, green, and blue at different intensities, you can make all the colors of the rainbow. So if you have a little bit more intense red, you shift it one way. If you have a little bit more intense blue, you shift it another way. And so we can make those. Well, anyway, these are just electrons being excited. So we can excite electrons in different ways. Like, for example, a lightning bolt. A lightning bolt is just an electric discharge, electric current through air. And so we can make a little lightning bolt. But the problem with lightning bolts are they're quite jagged. And then they're kind of hard to control. And the light that you get from a little lightning bolt would be inconsistent. It wouldn't be steady. So a lightning bolt would work, and you can make those in the lab pretty easily. In fact, I think we still have our power supply. We're missing a bunch of stuff. I usually show a little lightning bolt. I'll do it if I can find it. But we can make a controlled lightning bolt. The controlled lightning bolt is like this. We set up a tube with a couple of pieces of metal inside. This is going to be a glass tube. And then all we hook it up to is an electric power supply. The electric power supply is going to charge one of these pieces of metal positive and the other one negative. And so what that's going to do is if we can turn up the voltage high enough, and this is how a lightning bolt works, is once you get the voltage high enough, like 10,000 volts or 15,000 volts or something, you'll have it. 15,000 volts, the positive charge builds up, the negative charge builds up so strong that the electrons can travel from one electrode to the other. Well, if the electron travels this way, it doesn't necessarily travel in a straight line, like in air. If you look at a lightning bolt, does it go straight to the ground or does it have a circuitous path? It has a circuitous path because there are other atoms in here. There are going to be collisions and whatnot. So one of the things is to lower the pressure. If we lower the pressure, then that's going to result in fewer atoms of gas in here, although we do need some gas. And so here we'll put in a low pressure gas. If we put in a low pressure gas, then that will give a more straight line path here. And so we create this lightning bolt. But still, that's not going to generate much electricity. And so what we're going to do is we're going to put hydrogen gas in here. And if we turn up the voltage high enough, what's going to happen is the hydrogen gas is going to break up into hydrogen atoms. And so this is going to be high voltage, a lot of energy. And so the molecules break up into atoms. And then there are going to be collisions here. And the hydrogen atoms will get excited. And so we can do this. This would be an excited H atom due to the collisions. And the excited H atoms have electrons because there's one proton and one electron. And so when the excited H atom, what that means is the electron gets excited. And the electron gets excited, it goes to higher energy. And so the energy goes up. And so what we see is something like this. If this is the hydrogen here, sometimes the electrons get a little bit excited or a lot, depending on the collisions that are happening. But we have so many electrons in here that we're going to have electrons being excited to all different energy levels, as we say. You know, this hydrogen gets excited this much, this one, this much. And so eventually, we have electrons in all these excited states, and they don't stay there forever. They get excited by absorbing the power from our electrical power supply. Eventually, they'll drop back down. As they drop back down, then they'll emit radiation. And so here, this one didn't get so excited, it just emits infrared. Here, this one got more excited. You know, it's maybe emitting red, and then emitting orange, and then yellow, etc. So eventually what we got is we got all the colors of the rainbow. And so this would be called a hydrogen lamp. A hydrogen lamp should operate like the sun. The sun is one gigantic hydrogen lamp. And so the hydrogen atoms get excited, electrons get excited. Electrons get excited, they don't stay excited forever, and eventually it's going to start emitting all the colors of the rainbow because we have them. So it was expected that if you turn up the power high enough, you'll be able to excite this gas so it starts emitting white light. Just like if you heat the metal hot enough, it'll start emitting white light. And so this was expected to emit white light. You know, we just have to get things. We don't have to get it like the sun. You know, we just have to get the hydrogens hot enough to do it. And also, we don't want to emit much UV or X-ray. So you don't want too much power. This is what we call classical physics. Predicted this. Classical physics was developed, you heard of Newton? Newton's a very famous physicist in the 1800s. And so it's been around since the 1800s, classical physics, and a lot of laws that come with classical physics. And classical physics is what people use to get people to the moon and back. So classical physics is very powerful. But a good theory should be able to predict things, right? That's what theories should be able to do. Except this, which is a good theory because it gets people to the moon and back, to be able to predict. But this prediction failed. And so if the theory failed prediction, then how much confidence can you have in the theory? Not much confidence, say. So, but the way it failed and the subsequent theory that came after this didn't mean classical physics was wrong. Turns out classical physics is not wrong. Classical physics was just an exception. So classical physics, it turned out that classical physics is restricted. If we restrict classical physics for large objects, then it's correct. But if we try to apply classical physics to small objects, then it fails. And so classical physics can actually be derived from this. Quantum physics. Correct is probably not the right word for this. Quantum physics can be used to describe these observations and make predictions. Quantum physics can be used for both small and large objects. However, when you use quantum physics for large objects, then the equations simplify to classical physics, so we don't really need to use quantum physics for large objects, because we end up with the same equations as using classical. And so what happened is that the theory failed, and the theory failed. It had to be modified. Let's talk about the modification to this. when you visualize the atom, we have a proton. This will be the H atom. We have a proton here, and we have an electron. And one of the ways that the physicists visualized the electron in the atom was it was like orbiting around the nucleus, like so, let's say. And so the electron's orbiting around the nucleus like the Earth orbits around the sun. And if we excite the electron, what that does is it just increases the orbit, let's say. Just orbit a little farther and faster. This. So we can excite the electron to a higher orbit. And we can continue exciting the electron to higher and higher orbits, and depending on how fast the electron's moving. If it's not moving that fast, it's here. If it's moving faster and faster, it's going to orbit further and further away. As it orbits further and further away, it's going to have higher energy. And so we'll get higher and higher energies. Now, in classical physics, any orbit is fine. So if the electron's moving, let's say, at 5 miles an hour, it can move at 6 miles an hour. Or anything in between, 5.5 miles an hour, whatever, 100 miles an hour, 1,000 miles an hour. And so the electron can move at any speed you want. Just like if you're riding a bicycle, you can ride as slow or as fast as you can, right? And therefore, if we excite that electron, we can excite it to higher and higher energy, so it's going to start emitting all kinds of light. Infrared, red, violet, ultraviolet, even X-rays. Does that make sense? And so when we excite this electron in the hydrogen atom, it should start emitting white light. But that wasn't what was observed. And so this predicts, classical physics predicts the electron energy. It forms something called a continuum. A continuum means that all the energies are available. Continuum or continuous. Let's say continuum. When they made the hydrogen lamp, it looked awful. So this is the H lamp. The H lamp didn't provide white light. The H lamp provided like a violet light. It looks kind of violet. So to our eye, it appeared violet. But what we need to do is we need to pass this through a spectrometer, a visible spectrometer. I talked about a mass spectrometer. Mass spectrometer separates the atom based on the mass. A visible spectrometer is going to separate the light based on its wavelength. And so when we look at the spectrum from a visible spectrometer, what you do is you pass this light through a prism or a grating. And what that's going to do is it's going to separate it into the colors of the rainbow. It's not all the colors of the rainbow. It's not all the colors of the rainbow because it looks violet. And that violet is, a mixture. Maybe it absorbed all the colors except for violet. So if we only have one color coming off here, then a hydrogen is, in this case, is non-emitting. It's just emitting violet light. Or maybe it's emitting all the colors, except for violet. And so all those colors add up. Or maybe it's emitting just certain colors that add up to violet. And so what we do is we measure, it's going to hit the detector. This will be the detector here. And from the detector, we get an output onto the computer. The output onto the computer is going to be the spectrum. And so we get a little graphical output like this, the spectrum. And we have red, orange, yellow, green, blue, indigo, violet. And since it's emitting violet light, I expect it to have a peak here in violet, which just shows that it's emitting violet light and no other colors of light are emitting. But in this case, it's not. There's a very sharp emission of red light. Red light has a range of colors here, so we have different shades of red, going from infrared to orange. And so it has a very specific shade of red, and this is a pinpoint. And so it emits this color of red, but no other colors of red. I don't have any other colors here. So. There's another, here I do. Fortunately, somebody had this. It emits one color of green. The intensity of the green is less than the red. The red is quite a bit intense. Then it emits a certain color of blue. And then there's a very weak line of violet. And so the intensity of the violet is quite small, but this is going to be the highest energy light. This doesn't show much. And then when we add up these four colors of light, then these four colors add up to violet, oddly enough. Those add up to violet. And so that's why the lamp looks violet, and this is why you never want to read using a hydrogen lamp, because if you were reading using a hydrogen lamp, it would look pretty violet, and everything would look violet and probably strain your eyes a bit. So we call this the visible spectrum of the hydrogen lamp. So what does this mean? The interpretation of this is there are lots of blacked out regions here. These blacked out regions, these are called forbidden. Forbidden. And these other regions are allowed. So this is allowed. Allow, allow, allow. And everything else is forbidden, forbidden, forbidden. So what this means is that in the hydrogen atom, not all orbits are allowed. So we call this quantum. And rather than a continuum of energies, we have quantized energies. That is, quantized energies, we would have this as allowed. And then the next allowed one would be here. And then the next allowed one out here. But everything in between would be forbidden. this is forbidden. It is written in red, and the black is allowed. And so this means that if you're riding your bike, you can only ride it at 4 speeds. And you couldn't ride it. So let's say you're riding your bike and you're riding 5 miles an hour, that's okay. But you can't ride it 6 miles an hour because that would be forbidden. You would have to get to the next allowed. Let's say the next allowed were 10 miles an hour. So you could ride it at 5 miles an hour or 10 miles an hour, but nothing in between 5 and 10. Rather than a continuum of energies, we see quantized energies. Quantized just means they're forbidden and they're allowed. Quantized. So the energy is quantized rather than continuous. And so an analogy for that would be like this. If you have a ramp here, and we're looking at gravitational potential energy, and you could walk up the ramp, then this would be a continuum of gravitational potential energies. However, rather than a ramp, if you have stair steps, then this would be quantized. And so there are only certain energies that are allowed. You're going to be 1 step, 2 step, 3 steps up, or on the ground floor. So that would be the analogy. And so why is that? Why can the electron orbit here but can't orbit there? Well, that's what's observed. You know, what's observed is this: electrons can't orbit anywhere. And since they can't, it's just taken as is. Taken as is it's just taken without proof. This is what we call a postulate of quantum mechanics. Postulate of quantum mechanics is, well, that's the way nature behaves, therefore that's the way nature behaves. So Bohr came up with a model for the hydrogen. This is the Bohr theory. Bohr postulated that the electron can only occupy certain orbits around the nucleus. The first orbit is the n equals 1 orbit. That's the first orbit. And then the next possible orbit is what we call the n equals 2 orbit. This would be the next possible one. A little further out. It's going to be higher in energy. Then the next one is going to be the n equals 3. These aren't equal distance. You know, these orbits grow. And the next one will be n equals 4. And then after n equals 4, what comes next? N equals 5. And then after n equals 5, we're going to have n equals 6. So normally with hydrogen, the electron likes to stay down here in the lowest energy orbit. But if you start exciting the hydrogen atoms using electric power or whatever, or energy in the sun, fusion power, then what's going to happen is electrons get excited here, and not all the electrons are the same. You know, some get a little excited, some get very excited, depending on the energy that they absorb. But they don't stay there forever. So, for example, if an electron got excited from an n equals 1 to an n equals 2, and eventually drops back down. So what we could say is one way is called absorption of energy. And so the electron absorbs energy and gets promoted to a higher level. And what we do is we like to write this in terms of an energy level diagram. Energy level diagram. And so the electron likes to be down here at n equals 1 because that's the lowest energy. But it could get excited at n equals 2. Or the n equals 3. Now the spacing on the energies is not the same, just like the spacing on the orbits isn't the same. The orbit spacing grows bigger and bigger the higher we go. But the energy spacing kind of gets compressed. And so the biggest jump is from n equals 1 to n equals 2. And then n equals 2 to n equals 3 is a smaller gap. 3 to 4 is smaller. 4 to 5 is smaller. 5 to 6 is smaller. It gets smaller and smaller. Do you know how high it goes? What the highest one is? The highest one is n equals infinity. You know, when n equals infinity, do you know where the electron is? The electron's infinitely far away. If the electron's infinitely far away from the nucleus, then we call that ionized. And so if the electron makes it to n equals infinity, then it's free. It's free from the proton. And so this would be an ionized electron. It's completely broken off the atom. What would the energy be? You think the energy would be infinite, but the energy is not infinite. Here, n equals infinity. The energy, we actually call that zero energy, equals 0. And so when the electron's infinitely far from the nucleus and 0 energy, as we bring the electron closer and closer to the nucleus, then there's going to be a positive negative attraction, and the energy is lowered. And so as the electron gets closer and closer to the nucleus, the energy gets lower and lower. And so these energies are negative here, is because we set 0. This is an arbitrary 0. Right? It's like setting the temperature, the Celsius temperature. So what Bohr said is this. If an electron gets excited to the second floor and drops to the first floor, and so we have two processes occurring. We have absorption. The electron absorbs energy and gets excited and gets promoted to a higher energy, absorption. And so in order to absorb it, it can absorb energy in different forms. So for example, if you take UV light and shine it on this, it'll get promoted up to here. Or we can have it absorb energy in terms of collisions and that kind of stuff. And so it can absorb one form of energy and emit another form. When it emits energy is, let's say the electron got up to the second floor and eventually it comes back down and goes to the first floor. Well, there's going to be a jump, because it can't stop anywhere between here. So it's got to jump from here to here. Energy is conserved, first law of thermodynamics. And that emission is going to occur as UV, in this case, ultraviolet, because this is a pretty big jump here. And so we emit UV light. If the electron gets all the way to the third floor and drops to the first floor, that's going to be UV too. But what can happen here is electron can get to the third floor and drop to the second floor. If the electron gets to the third floor and drops to the second floor, it emits violet, or actually no, red. This emits red. If the electron gets excited to the 4th floor and drops to the 2nd floor, obviously it could go to the 3rd floor, or it could go all the way to the 1st floor. But if it goes to the 4th floor and goes down to the 2nd floor, it emits green light. This will be green. If the electron gets excited to the 5th floor and drops down to the 2nd floor, this is blue. And then if it goes all the way to the 6th floor and drops to the 2nd floor, then this is what we call violet light here. This would be violet. So what Bohr did was he said that the colors that we see in the spectrum are due to these. These are called transitions, electron transitions. And so color is due to electron transitions. And the electron transitions are between these energies, which relate to these orbits. And so an electron's in the 3rd orbit drops to the 2nd orbit, that's that there. Electron transitions in the orbits. Or the 4th orbit to the 2nd orbit, 5th, etc. And so these are the colors here. Let's see. And so emission is when we go down here. Green is higher energy, shorter wavelength, higher frequency. Blue, and violet. And so we only see 4 colors because there are only 4 gaps here that are in the visible region. The other gaps are in the ultraviolet and in the infrared. The infrared would be something like this. Let's say we're on the 4th floor and we go to the 3rd floor. 4th floor to the 3rd floor is going to be even smaller jump in energy. What's smaller than red? Well, it would be infrared. And so we're going to have things in the ultraviolet and the infrared as well as the visible, but there are only 4 lines, we call these lines, in the visible. And the 4 lines in the visible for the hydrogen are red, green, blue, and violet. And these have a very specific wavelength. So for example, the wavelength of the red is 656, and nothing other. I think this is 589. The units for wavelength are nanometers. I would show it to you. I don't have the wavelength memorized, but the wavelengths of the spectrum, and so when we look at the spectrum, that's why we end up with this. This would be it. And the units we use for the spectrum are going to be, red starts off at 760 nanometers of wavelength. And then at the end of violet, we have 390 nanometers. And so the visible light range is between about 800 and 400 nanometers. So this is about 800 to 400 nanometers. In the center of it's green, let's say, and that's around, what's in the center of this would be 600, around 600 nanometers would be around here. So we can kind of guesstimate the light is. If we had a white light, which we expect, white light would show all the colors. This would be the emission spectrum. We have 2 types of spectra, absorption and emission. So this would be emission spectrum. And it just shows what color is light. And so white light would be something like this. This would be white light. it emits all the colors. It's a continuum. Okay. Continuum. However, the hydrogen lamp emits just four: the red, the green, the blue, and the violet. This is the H lamp. And those colors combined add up to this kind of violet purple light. Let's see. So basically, just a model. Once they did the physics for this, they could calculate it. They could do the calculation and figure out what the wavelengths are. And they could predict all the wavelengths in the infrared and all the wavelengths in ultraviolet as well, using the math from this. I don't think we're going to get into the math for this at all. Let's see. Uh-huh.
As the distance of the emission from level to level increases, the energy increases, the wavelength decreases, and the frequency increases.
Mm-hmm.
Okay.
Right.
And so, if let's say you were at like N99 and you dropped to N2, would that be like ultraviolet?
Yeah, or maybe even X-ray.
X-ray?
Yeah.
Is there like a specific level that defines X-ray, gamma ray?
Yeah, there it is. It turns out that for hydrogen, if you are at N99, if we measured it, it turns out it's not. It turns out it's still ultraviolet. In fact, we can calculate it. We can calculate and this is what you do in Chem 1A. In Chem 1A, you'd calculate what kind of light would take to go from n equals 1 to n equals infinity. And when you do the calculation, it turns out ultraviolet is enough. Maybe not the lower energy ultraviolet, but the higher energy ultraviolet is enough to knock the electron off the hydrogen atom. We don't need X-ray. We don't need gamma rays. X-rays and gamma rays will do it. They'll eject the electron off the atom and then give it some kinetic energy to boot. And so, but for other elements, yeah, to get to N99, you could need higher energies of electrons. For metals, you don't. Metals it's easy to get to N99. They're all compressed, lower in energy. So it depends on the element. Did this thing come back on? Oh, it finally started working again. Yeah, this wasn't working. Some kind of animation. Well, anyway, this is the picture that comes up. You can see, if you want to see this, they have animations of this transition, but I'm not going to spend too much time on the Bohr model here. But there's a lot of stuff in the Bohr model. So now we have the Bohr theory, what's going on with electrons. Electrons can't have any energy. And so what we should do is we should predict if we make the lamp out of something else. So for example, if we make the lamp out of, instead of hydrogen, if we make the lamp out of neon, neon has electrons. Neon you should be able to excite. You should be able to excite the electrons at any energy you want. According to classical physics, you should. And so a neon lamp should emit white light, but does a neon lamp emit white light? No. A neon lamp emits kind of this kind of orange light. And so is it because it's only emitting orange? No, it's emitting certain colors. It's actually emitting a bunch of different colors that all add up to orange light that you see in neon or orange, whatever it is, the color.
Remind me of experiments used to see the different colors, like if we were to look at the fluorescent
Mm-hmm.
lights, and it'll give us the spectrum.
Mm-hmm.
What do you use for that again?
A spectrometer, a visible spectrometer.
Visible spectrometer, is that like the glasses or?
Mm-hmm. That could be like the glasses, you know. The instrument would be your eyes would be the detector, and the glasses would be. In fact, I have glasses. We can take a look if you're interested.
That'd be cool. Is this related to like why different gases that are in neon emit different colors?
Yeah, exactly. It's because not everything's going to have the same allowed and forbidden orbits, and the orbits are different. So the orbits in neon would be different than the orbits you'd find in hydrogen, which would be different than the orbits.
It's how far out?
Yeah, right. How far out? And neon has more electrons than hydrogen.
Seems like they're able to pretty much get like any color.
Yeah, they can get a lot of different colors. There are other ways they can get the colors too through LEDs, but the situation is we should be able to use the Bohr theory to predict the color. We should be able to use Bohr theory to predict the color of neon and then figure out what the spectrum looks like. You know what all the lines look like there. But when they tried to apply Bohr theory to neon, it failed. And so classical physics failed. And then the Bohr theory seemed to work for hydrogen, and then it failed for everything else. They tried it on the next most complicated, which would be helium, and it failed. And so Bohr theory has been abandoned. You'll see lots of videos on the Bohr theory, the Bohr model. And you'll have this picture. People always use this picture showing the atom. Have you seen this one? Where you have electron here. The orbits don't have to be planar. You know, the orbits can be in whatever plane you want. Have you seen this picture of the atom?
Yeah.
Well, that's wrong because we don't have orbits. At least wrong in thinking this is the Bohr. But there's a problem with Bohr because if the theory can't predict, then you can't have much confidence in the theory. And so the Bohr, the problem with the Bohr is a major problem. And for Bohr, the major problem was it seemed to only work for hydrogen. It seemed to work, but it actually was incorrect. Let's just say seemed to work for hydrogen only. Couldn't predict anything else. And so to make a long story short, Bohr, not everything about Bohr was abandoned. Some things about Bohr were retained. And so two additional people, there's Niels Bohr is the physicist who worked on this. But we had two more people come along and to develop what we call the modern theory of quantum. And so this is quantum version 1. This will be quantum version 2. Quantum just means that, not all the energies are allowed. Some are allowed, some are forbidden. Versus continuum. Classical physics was continuum of energies were allowed.
Is the word quantum derived from it being like only allowed in certain quantities?
Yeah, right. Only allowed in certain quantities. That's what it is. Uh-huh.
light and everything for the colors. Do you think how it was first discovered was using iridescence? When they see, like, you know, for instance, oil or soap bubbles, and you could see.
Yeah, those experiments were done by like Newton and others, you know, in classical physics. In classical physics, they saw all the colors of the rainbow, so they started playing with prisms and this kind of stuff, oil droplets to spread out the light into the component colors. So that's been around. The problem is, let's say the sun were behaving. You know, the sun is a giant hydrogen lamp. And so why does the sun's hydrogen lamp behave so differently than the hydrogen lamp we have here on Earth? And so I'll talk about that. And so in quantum version 2, we have two important additions. One is de Broglie, and the other is Heisenberg. So I'm going to just kind of do the short version of this. De Broglie is the wave-particle duality. Of light and matter. Heisenberg is the uncertainty principle. Uncertainty principle, we have to talk in terms of probability. So we have to talk about interference. That is, two waves interacting with one another. And let's say we have this wave plus this wave. What would the resulting wave look like? If we have those two waves adding up, then what results is what we call constructive interference. That is, the two waves will constructively combine. We'll get something like this. That is, the peaks on these match up and the valleys on these match up. If the peaks and valleys match up, then the peaks get amplified and the valleys get amplified. However, if they're mismatched, even by a little bit, if they're mismatched, we'll get destructive interference. And I'll just exaggerate the mismatch, but it doesn't have to be this mismatched to get destructive interference. It just has to be slightly off, and then eventually they'll be completely off. And that is, let's say on this wave here, I combine it with this wave here, so that the peak on one wave matches a valley on the other wave. And what we have is these will cancel each other out. So it's just, they cancel. Mean nothing. And so this is what we call destructive interference. So what de Broglie says is that electrons have wave properties too, and the wave properties we have to account for. And so if an electron is traveling like this, and the second electron is traveling like this, let's say, then they would interact with each other constructively versus something like this. Well, the electrons themselves aren't destroyed, but what happens is this. If an electron is confined to an atom here, then we have to consider the wavelength of that electron. So let's say the electron's traveling this path like this. Then this would be constructed, and this would be allowed. We have to factor in the waves of the electron, the wave of the electron. However, if the electron were just slightly higher in energy, then eventually we're going to have a mismatch. And if we have a mismatch and this carries on like this, then it's going to cancel out. And so this is going to be where this, these are called half wavelengths, each of these humps, where the half wavelengths just match up. And here there's a mismatch. And we have destructive. This would be forbidden. This is allowed. This would be constructive. And so this would be the atom here. But we can see this happening in this here. Let's go with 1D.
What we have here is a frequency generator connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now, waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called a second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle is a node. So we have three nodes for this one. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
So that's forbidden there, and then this is allowed.
And there we go.
So all the energies in between this frequency and the other frequency are
Start
forbidden.
of a jump. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, and what is that, around 25.5? And there we go. So that's the third harmonic. How many wavelengths is it? 12? It's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with a high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and derivations.
We're not going to do any calculations. We're just going to look at quantization here. And so n equals 1 is allowed. N equals 1 consists of 1/2 wavelength. So we put that. That fits in between the ends of the string here. Or we could have 2 half wavelengths or 1 full wavelength. So n equals 2 is allowed. But we can't have anything in between. So if you tried n equals 1.5, 1.5 half wavelength, it doesn't work. Or n equals 2.1, that's not going to work. All those are going to be forbidden. The next allowed one will be n equals 3. Well, the same thing happens with electron in an atom. Electron in an atom is going to have allowed and forbidden things like this. Okay, that's for one-dimensional. Let's go to 2 dimensions and take a look at what's allowed and what's forbidden in 2-dimensional. Standing waves. So this is just a metal plate. So this is allowed here. And then they change the energy, the frequency, a little bit, and then it'll go for. So this is kind of forbidden, and then let me turn down. Going higher and higher energies, only certain energies are allowed. This is an allowed energy because you get those waves in there. This is allowed. When it goes forbidden, allowed. As we go higher and higher in energies. Those energies are going to depend on how big the plate is. Smaller plate, bigger plate. They all have different, what we call resonant frequencies. So we go into very high energies here, at least in audio side. where the salt accumulates is called a node. So the plate's either going to be higher here or lower there, and then goes through called a node. This is another video, same thing. There's lots of these videos. Uh-huh.
Reminds me of in physics when you use tuning forks for wavelengths and harmonics.
Yeah, it's the same thing. It's the same thing because each of these will have allowed, and it depends on how big this is, what's allowed and what's forbidden. The same thing with electron and atom. Depends on how big the atom is. That's going to change
Very
things.
similar to how fluorescence units work too.
How what?
Fluorescence units.
Oh yeah.
Completely reliant on this.
Right, on these standing waves and this kind of stuff. Yeah, that's totally true. So we see this in nature, obviously, and then we see this in electrons here. So let's take a break here, and then we'll start again after the break. That is, why is sunlight a continuum, but a hydrogen lamp is discontinuous, quantized. And the reason has to do with the size. When we get to, let's say, higher and higher, let's say there were 1,000 half wavelengths here. So if we go from 1,000, n equals 1,000, to n equals 1,001, do you expect a big jump in energy if we just fit one more half wavelength in there? No. I mean, in fact, the difference in energy is like negligible. When we get to 1 trillion, they 10 to the 12th, and then we go to 1 or 2 trillion, I mean, like 1.01 trillion or something. We add one more half wavelength. So if we have 1 trillion half wavelengths here, and we go to 1,000,000,001 half wavelengths, then you aren't even going to be able to tell the difference in energy. They're so close to one another. Does that make sense?
The greatest energy jump would be from 1 to 2.
Yeah, right. And so what we see is this. In tungsten metal, or in the sun, there's a huge difference here, but for the electron, it's kind of the same. In tungsten metal, the electrons are free to move in the filament, and they aren't confined to the individual atoms here of tungsten. If the electrons were confined to an atom of tungsten, then it would be stuck. We'd call it in a small box. So think about a whale. If you had a whale at SeaWorld, a whale at SeaWorld is very constricted because does it have much room to swim? Let's say. No. And so the whale, if the whale's moving back and forth in a swimming pool, can it move any speed it wants? No. And so, whereas if you had a whale in the open ocean, then it would make a difference. And so if we have a small box, that is a small pool, versus a large box, it makes a huge difference. So an electron confined to a small box would be like an electron confined to an atom, electron in an atom. Then we're going to notice the wavelength, the quantization here. This would be like an electron confined to an atom here. Actually, both of these are. But as we notice that, however, if you have an electron, what we call a free electron, like in the sun or in a metal, this would be a free electron. The free electron can move any speed. This would be like a whale in the open ocean. The whale in the open ocean can move any speed it wants, as fast as it wants. So a free electron can move any speed. That is, it can have any energy. Whereas when you confine that electron into a small box, then it's constricted. So this is like the whale. The whale can't move any speed it wants. It can go as fast as it wants. Though it's not a perfect analogy, that would be it. And so these things weren't noticed because normally physicists don't deal with small objects. They deal with large boxes. When dealing with large boxes, then energy is a continuum. And so even a baseball has wave properties, but a baseball, on a baseball field, that's a large box. And the wavelength is very small for a baseball compared to the field. But an electron, it does have a very small wavelength, but it has a very small box. Whereas a baseball has a very large box compared to its wavelength. And so here it's going to make a significant difference. And so this is why a lot of people say, quantized things don't really come into play until the size of the box gets extremely small. Quantum for very small things, because for very small things, then the wave properties become significant. But for very large things, the wave properties are kind of insignificant because the wavelength is so small that it doesn't impact what's allowed and what's forbidden because the energies are so closely spaced together. Okay, so what we're going to do is we're going to map out the allowed wave for the electron, and we call these wave functions. But wave functions is too much. A wave function is called an orbital. And the orbital, these are the allowed states for the electron in an atom. So we map this out in something that's called an energy level diagram. And the energy level diagrams in your book aren't that great. The energy level diagram in the supplement is much better. So let's take a look at this. Yeah. So there's a section in the supplement called quantum. You can find it. You might have priced it. I did. So this is it, and we give special symbols to the loud wave functions of it. And so this is the energy level diagram for an atom. And so the lowest energy that's allowed is called the 1s orbital. And what does the 1s orbital look like? The 1s orbital looks like this. So if I have the nucleus here, it's just spherical in shape. But there's one other thing. It's not orbiting. And so the electron can be anywhere inside here. And the one other thing is, de Broglie talks about the wave properties of matter. You know, everything has wave properties, like a baseball or an electron. Heisenberg talks about the uncertainty principle. The uncertainty principle is the electron is somewhere in here, and it's going to have the wave properties. Yeah. It's somewhere in here, and we set a boundary. The boundary is, there's a 95% probability it's going to be within the boundary, and a 5% probability it's outside this boundary. And that boundary is usually the way we visualize the orbital. It's this is the 95% boundary. It's a probability boundary. And so the electron's like a bird. You know, let's say the bird's nest is here at the plus. And let's say the bird has a certain amount of energy. It doesn't have that much energy to travel that far from the nest. So you're going to find the bird kind of close to the nest, mostly. Sometimes you'll find the bird far out, but that probability is going to be very low because the bird doesn't have enough energy to travel very far out. But we'll set a boundary here. This 95% boundary means the bird is going to be found within here with 95% probability. But the weird thing is can you predict where exactly the bird's going to be? Let's say we pinpointed the bird here. Okay, 5 seconds later, can you tell me exactly where the bird's going to be? Yeah, well, the same thing with electron. If we pinpoint the electron here, 5 seconds later, I can't predict where it's going to be. This is the Heisenberg uncertainty principle. Where we don't know exactly where it's going to be. Whereas in the Bohr model, we could predict where it's going to be because it's just orbiting around an orbit. If it's orbiting around an orbit, then you can predict where it's going to be 5 seconds later if you know how fast it's going. But with orbitals, we don't. And so we talk in terms of probability. So 1s orbital has a spherical probability in 3 dimensions. And so it's just a spherical orbit. And so it looks like this. It's low energy, so it can't get very far from the nucleus. So that's what it would look like. A 2s orbital, when you're giving the electron more energy. So if the bird has more energy, it can venture farther out from the nucleus. And so the next allowed one is called a 2s orbital. And basically it's kind of the same shape, except now the bird can get farther away from the nest. And so when we look at the probability of distribution, this would be a 2s here. This would be a 1s here. Now when we look at the density of dots is going to tell us, okay, the bird's here, the bird's there. And so with a 2s, it can be further out. Like this. But outside this boundary, there's very low probability. And so 2s orbital, what we say, is bigger than a 1s orbital. It's just kind of, but it's still spherical in shape like that. Now the next orbital is called 2p, and the 2p orbitals are kind of weird. And so I'm going to write it over to the right here, like they did here. It's just higher in energy, and it's going to have different shapes. There's actually 3 of them that it can adopt. So these are the 3 2p orbitals we call. The first 2p orbital has like this dumbbell shape. So, like this. The second 2p orbital has the same exact shape, except a different orientation. And the third 2p orbital has the same exact shape, but a different orientation. So, you know, these would be on the x, y, and z coordinates, let's say. And so here, try to draw this here. We'll have one 2p orbital, and I'll draw it like this. That has like this figure 8 shape or dumbbell shape. And so the weird thing about this distribution is it's going to be confined. So we have 95% probability of finding an electron in this lobe, we call this a lobe here, and in this lobe. But outside this region, just a 5% probability. Here, this lobe and this lobe. Here. This lobe and this lobe. And so that would be like this. This lobe here and this lobe. And so we have one, let's say, on the Z plane, X plane, the Y plane, or axis, let's say, not plane. And so that would be it. And then after the 2p, we have the 3s. And the gap is going to be a little smaller. The 3s is just a bigger version of this. But there's something called node in there. And then we have the 3p here. And we can map out all these, what we call energy levels or orbitals here. The 3p are bigger versions of the 2p. There's more to it than that. And then we have the 4s, the 4p, the 3d, the 5s, the 5p, the 4d, etc. All the way to infinity. And so there are a whole bunch of allowed states here. And given this name. So this is called the energy level diagram for multi-electron monatomic species atom. Okay, I said we weren't going to do any math, but we're going to do a little bit of math. These allowed states are called orbitals. And they come from the mathematics of quantum mechanics. And so there's somebody called Schrodinger who came up with the equation that combines everything in there. Schrodinger equation is going to give us the orbitals. So we'll use a map to figure out the orbitals. So, we're not actually going to do the math. When you do the Schrodinger equation, the math, there are an infinite number of allowed orbitals. And there's an infinite number of forbidden energies. And so the allowed orbitals will have certain mathematical restrictions. So from the solution to the Schrodinger equation, we can get individual solutions or we can get a mathematical equation that tells us all those solutions. So from the solution to the Schrodinger equation, there are mathematical restrictions. There are 3 or 4, 3/4 mathematical restrictions. We call these mathematical restrictions quantum numbers. The quantum numbers have special restrictions to them. The first 3 quantum numbers define the orbital, NLM. The fourth quantum number tells us about the electron in the orbital. And so N, L, and M will tell us. So for example, the 1s orbital has the three quantum numbers 1, 0, 0. This is N, L, M. So N is equal to 1, L is equal to 0, M is equal to 0. That's allowed. The second orbital that's allowed is a 2, 0, 0, NLM. This one, the 2p, we have the 2, 1, 1, the 2, 1, 0, and the 2, 1, negative 1. And this just comes from algebraic restrictions on N, L, and M. In other words, these are just mathematical patterns. So, N, let's talk about N first. What is N? This is from the supplement. This isn't in the book. But this is to make Chem 1A a little bit easier. You don't have to go through the whole thing in Chem 1A. You go through a little bit in Chem 4. So N is called the principal quantum number. And the mathematical restrictions to N is just shown here. N can be an integer from 1 to infinity. But it can't be anything in between. So let's say I want an N of 0.5. An N of 0.5 is forbidden. Or an N of 0.99 or an N of 1.5. All those are forbidden. And so these are allowed. If you try to put a forbidden N in there, what happens is it doesn't solve the Schrodinger equation. The Schrodinger equation forms the basic foundation of quantum physics. And so this just comes from the math. You don't have to worry about where it comes from, but you need to know that N goes from 1 to infinity. And anything else is forbidden. L is called the azimuthal quantum number or the angular momentum quantum number. And the mathematical restrictions are here. L takes on all values. So these are allowed. All from 1, 2, 3, ... up to infinity. So there are an infinite number of allowed ends, but there are also an infinite number of forbidden ends, like 1.5. L takes on all values from 0, 1, ... to a max of n minus 1. That's just the way the math works. So if n equals 1, then the L value we can have is 0. We can't have an L value of 1. So when n equals 1, the only L value that's allowed is an L value of 0. We can't have an L value of 1. But when n equals 2, there are 2 allowed L values. The first allowed L value is 0. So we have 2, 0 here. The second allowed L value is 2, 1. But we can't have 2, 2. 2, 2 would be forbidden. You see that, how that works? And so we have the 2, 0 and the 2, 1. Now, the L is given a letter. So if L equals 0, we call it S. If L equals 1, we call it P. If L equals 2, we call it a D. If L equals 3, we call it F. And then it goes alphabetical beyond that. And so it goes S, P, D, F, A, B, C, D, E, F, G, G, H, I, K, etc. Alphabetical. And then we have N next. N is called the magnetic quantum number here. And M can take all values from minus L to minus L plus 1, etc., through 0, etc., to plus L, plus L minus 1 up to L. And so in other words, it takes on all values from minus L to plus L, including 0. So here in the first allowed one, we have an L equals 0. If we have an L equals 0, then we can go from plus 0 to minus 0. And so there's only one, and that would be 0. So when n equals 1, we have L equals 0 and n equals 0. This is the only allowed orbital with an n equals 1. But when we get to n equals 2, we have more allowed orbitals. That is, when n equals 2, we can have L equals 0. Well, if L equals 0, then the only value for n is 0. We go from negative 0 to plus 0. However, when we have n equals 2, we can also have L equals 1. If L equals 1, then we can go from minus 1 to plus 1. So we go from minus 1 through 0 to plus 1. So we have 3 possible values for this. Does that make sense so far? So doing this, we can build up the entire map of the this. So what does that look like? That looks like this. Now the energies, the main thing is, as we go up, we go higher energy. And so as n increases, the energy increases most significantly. As L increases, this is L equals 0, this is L equals 1. As L increases, the energy goes up. So here I have N3, L0. That's what all these have in common. These are all L equals 0 or all equals S orbitals. Over here, we have all the p orbitals, or the L equals 1. When L equals 1, m is minus 1, 0, 1. L equals 1, minus 1, 0, 1, etc. So these are what we call the p orbitals. But when n equals 3, we have L equals 0 is allowed, the s. L equals 1 is allowed, the p, and L equals 2 is allowed. L equals 2 is called the d orbitals. And the d orbitals are going to be from minus 2 to 2. So we go, this would be the 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. And so let's build up the energy level diagram higher. Now, the energies we could calculate using the Schrodinger equation, but we're not going to do the calculations. What we're going to do is we're going to use this to figure out what the energies are. And this is this, we'll call a pyramid. 1s, 2s, 2p, 3s, 3p, 3d. And so here L equals 0, L equals 1, L equals 2, 4s, 4p, 4d, 4f, L equals 3, etc. So when we build up a pyramid like this, we can get the order. This is the energy ordering. So we go 1s, followed by 2s, followed by 2p, 3s, followed by 3p, 4s, 3d, 4p. So it goes through this kind of pattern like this. And so let's take a look at what this looks like. So 1s orbital goes here. The 1s orbital is also called the 1, 0, 0 orbital, followed by the 2s orbital, which is here. This will be called 2, 0, 0. Followed by the 2p orbitals. And now there are 3 2p orbitals. What are they? The 3 2p orbitals will be the 2, 1, 2. I mean, not 2, 1, 2, 2, 2. 2, sorry. 2, 1. 2, 1, 1. 2, 1, 0. And 2, 1, negative 1. It doesn't matter what order you write them in. So those would be the 2p. And then the next allowed orbital will be the 3s. The 3s is a 3, 0, 0. Okay, n is equal to 3, we're allowed 0, we're allowed 1. And so this would be the 3p. The 3p would be 3, 1, 1, 3, 1, 0, 3, 1, negative 1. Okay, you'd expect the 3d to come next, but the 3d do not come next. What comes next is the 4s. So we'll stick the 4s in here, which is the 4, 0, 0. And then oddly enough, the 3d come next. And so I'll write the 3d. Now, how many are there? The 3d is going to be 3, 2. So this will be 3, 2, 2, 3, 2, 1, 3, 2, 0, 3, 2, 1, negative 1, 3, 2, negative 2. So there's going to be a total of 5 of them because we're allowed to go from plus L, which is 2, to minus L, which is negative 2. And so that tells us there's going to be 5 d orbitals versus the 3p orbitals. And then the next orbital is the 4p orbital, which is going to be higher energy, according to this. And so when we look at the 4p, we'll go from 4, 1, 1, 4, 1, 0, 4, 1, negative 1, etc. And so you should be able to build the energy level diagram to here. And so we're just using the mathematical constraints of the Schrodinger equation to figure out how many we have. And so N tells us the principal energy. L tells us the shape. So S orbitals are all spherical, and they're just going to grow in size. So N, energy, L, shape. Now the shape of the P's are different, so they're going to have slightly different energies. The shapes of the P's look like this, and then they grow in size. Oops, they aren't all the same orientation. M tells us, the magnetic quantum number tells us the orientation. Sorry, need to redo this. These are going to have 3 different orientations given by 3 different M values. The D's have a different shape. D's are cloverleaf in shape. Let's try to redraw that. So they kind of have a cloverleaf shape to it. Most of them are cloverleaf. There are some weird ones, like this one. Weird one. Maybe I'll write that at the end. Essentially, 4 of them are like cloverleafs, and the 5th one's like a p orbital with a hula hoop in it. So we can take a look at that here. These are the d orbitals over here. Most of them are cloverleaf shaped, 4-leaf clover, and one with that looks like a P with a hula hoop. These are called lobes. You know, they have different lobes. And so we can map this out. These are all allowed energies for the electron. So the electron can occupy this, or it can occupy any of these higher energy orbitals. And so what happens is the electron transitions get much more complicated. Do you see how much more complicated they get? Because there's so many more energy levels here that the spectrum is going to be a lot more complicated than what you'd predict if you just had single orbits. And so when we look at the, and this works for hydrogen, this works for many others. Mm-hmm.
Why is there is kind of what is there like some sort of pattern that's causing that shape? Why is it this weird?
Yeah, that's because of this. You know, why is there a weird shape?
Oh, it's the resonance.
Yeah, it's the resonance. It's like, yeah, you get these weird shapes when this happens. this is the weird shapes. So these are called nodes here. And then, you know, they go up. These are like waves, down, and then up. See? So it go up, down, down, up. How it's vibrating. And so this is the same kind of thing. These electrons have wave-like properties. These spherical ones are just up. This is like, you know, halfway. Okay. This one's up and down. So you get this figure 8 deal. And then these are more complicated. And so this is just because of the wave properties. That's what gives them these weird shapes. The wave properties of electrons. And so it's weird, basically. Let's see. Some of these get really weird. So I have this video that shows the shapes of these very high energy orbitals, but it's on a video cassette, which we don't have anymore. But I'm pretty sure probably somebody put it on YouTube. Yeah, VHS, exactly. Do you see these weird shapes over here? These are the higher energy ones, so it just keeps getting weirder and weirder. Look at this one.
Did you realize that not all electrons in an atom have the same amount of energy? It's true. The amount of energy of any given electron depends on where it's located within an atom.
This is totally wrong, right? This is the Bohr model. This is completely wrong.
Electrons reside in principal energy levels, or shells, which surround the atom's nucleus at various distances. Each shell is further divided into sublevels of increasing energy, named S, P, D, and F. And these sublevels consist of orbitals, specific regions of space within the sublevel where an electron is likely to be found. Named for their energy sublevels, there are 4 types of orbitals: S, P, D, and F.
There are 4 types of orbitals for the elements in the periodic table, but there are more if you excite the electrons. So there's going to be, after F, there's going to be G, H, I, J, K, et cetera, et cetera. There are infinite number of orbitals.
What's after that?
After Z, you go double A. Yeah. A, then A, B, A, C, A, D.
What happened to reach a ZZ?
Yeah, you have to go to AAA, etc. You know, it just has to continue that way. Otherwise, you're right, you're going to run out.
Is there any examples of things that are like what's the that's recorded? Like what's the highest number of?
Well, in the periodic table, the electrons, there are a lot of electrons, but if you fill all the orbitals in the periodic table to the lowest energy, then they go up to the F. The F's the highest they go on the periodic table. But if you excite the electron can go to higher energy empty orbitals. And so those higher energy, yeah, there's examples of that and people can calculate. This is all done by calculation. You can calculate it quite easily. It's not that hard to calculate. These 4.
Each orbital type has a unique
if you make certain assumptions.
shape based on the energy of its electrons. The s orbital is a spherical shape. The p orbital is a dumbbell shape. There are 3 p orbitals that differ in orientation along a 3-dimensional axis. There are 5 d orbitals, 4 of which have a clover shape with different orientations, and 1 that is unique. There are 7 f orbitals, all with different orientations. Why are there different orientations? Because the atom is 3-dimensional. And notice that the further away an orbital is from the nucleus, the more complex its shape is. Why? Because its electrons have more energy.
There are two things that influence the energy. The main thing is N. The higher the N, the higher the energy. The second thing is the shape. It's not just the shape, because here it depends on the energy. So 2p is slightly higher in energy than a 2s. But 3p, is lower in energy than a 4s, but it's higher in energy than a 3s. So it goes like this. So the primary thing with energy is N. Secondarily, L. L is the shape, the orbital. M just tells us the orientation, the number and the orientation. And so when we get to F orbital, the max L is 3. And so we'll go from -3 to +3. Going from -3 to +3, there's 7 values. -3, -2, -1, 0, 1, 2, 3. So that's altogether 7 values. Therefore, there's 7 orbitals. Each of those orbitals will have a different orientation. I didn't draw the F's here, but you just need to know up to 4p. Now, he talked about shells in that. The shells are going to be like this. Shells are a set of closely spaced orbitals. So this we call the first shell of orbitals. This is going to be the second shell of orbitals here. And this will be the third shell of orbitals here. And this will be the fourth shell of orbitals here. In each shell, we have subshells. So in the first shell, the only subshell we have is the 1s. In the second shell, we have 2 subshells. We have the S subshell and the P subshell. The P subshell has 3 orbitals in that particular subshell, but so it would qualify as 2 subshells. In the third shell, we have 2 subshells, the S and the P. However, in the fourth shell, we have 3 subshells, the S, P, and the D. And then we can continue from there.
So you might get into this, but can you show this using Hund's rule?
Yeah. We're going to, the next thing we're going to do is we're going to put electrons here. Now, we could have excited electrons in any of these. In fact, n equals infinity. If we excite the electron to n equals infinity, do you know what happens? If we take an electron and excite it to n equals infinity, it becomes ionized, becomes completely detached from the atom. And so that's called ionization. But what we can do is we can put, it depends, if we have 1 electron, where do you think that electron would be the most stable? Probably closest to the nucleus. So if we have 1 electron, we put it here. We call this the ground floor or the ground state. The ground state is, could we put more? Yeah, if we have 2 electrons, I'll put them here. What if I have 3 electrons? If I have 3 electrons, I should put them here. In fact, if I had 100 electrons, shouldn't we put all 100 electrons in the ground state? We can't fit them all. Do you know how many electrons we can fit? Only 2. We can fit 2 electrons in each orbital. Do you know where that comes from? What that's called? It comes from quantum mechanics. Okay, so there are a lot of names in quantum mechanics. So what were the names so far? Bohr. But what do you know about Bohr? He was wrong, unfortunately. But he's still famous. So, because some of the stuff was right, and Bohr was the first quantum theory that came out. Then after Bohr, we had de Broglie. De Broglie talked about the wave-particle duality. Electrons have wave type properties. And then after Heisenberg talked about probability. These orbitals are just 95% boundaries where, we'll have a 95% chance of finding electrons. And then after Heisenberg, we had Schrödinger. The Schrödinger equation is where we can figure out all the allowed orbitals. Okay, now there are more. Unfortunately, there are more names. When we put electrons in orbitals, we have to worry about Pauli. And so the first thing is the Pauli exclusion principle. The Pauli exclusion principle says that the electron has a quantum number itself, and the electron can be s plus 1/2 or s minus 1/2. All others are forbidden, and so there are only two allowed states for the electron in an orbital. It could be plus 1/2 and minus 1/2. And these correspond to something called electron spin. That is, electrons generate a magnetic field. This is purely quantum mechanics from the spin. So one of these will have the north pole up, the other will have the north pole down. That's it. And so what the Pauli exclusion principle says is this. An electron is defined by 3 quantum numbers for the orbital and 1 quantum number for its spin state, that is up or down. So an electron in an atom has 4 quantum numbers, 3 for the orbital, 1 for the spin. What Pauli exclusion principle states is that no two electrons in the same atom, in an atom, can have the same set of 4 quantum numbers. So we represent electrons using arrows to represent the spin. So I put an electron here with the spin up. So I'll write an arrow pointing up. That represents an electron with a spin plus 1/2. So the orbital is a 1, 0, 0 orbital, and the spin quantum number is plus 1/2. And so the 4 quantum numbers that define this electron, this arrow, is 1, 0, 0 plus 1/2. And so we call that the 1, 0, 0 plus 1/2 electron. 1, 0, 0 tells us it's a dress, essentially, and the plus 1/2 tells us it spins up. Okay, I can't have another 1, 0, 0 plus 1/2. So the next electron, I have to have a different spin. And so the next electron will be spin down, let's say. And this one will have a negative 1/2 spin number. And so this will be a 1, 0, 0, negative 1/2. If I put in a third electron, I don't have any other spins I can use. The 2 spins I can use are plus 1/2 and negative 1/2, so a third electron won't go in here. Because a third electron would have to have one of these spin states, and I'd be repeating it. So I can't have 2 spin ups or 2 spin downs in the same orbital. So if I have hydrogen, it's okay. Hydrogen can be here. And if I have helium, helium has 2 electrons. I can put both those electrons here in the 1s orbital. However, if I go to lithium, lithium has 3 electrons. And there's not enough room to fit 3 electrons here. So the third electron has to, unfortunately, go to the next higher energy orbital. And so for lithium, it doesn't matter if it's spin up or spin down. It's going to be the same energy. But normally people just write it spin up. And so if I go to lithium, I'll be here with 3 electrons. And so I have to go into the second shell. And so the first shell is filled with helium. And so I go to lithium here, starts filling the second shell. And this orbital can contain 2 electrons, 1 spin up, 1 spin down. So if I go to beryllium, beryllium is going to be spin down like this. That's 4 electrons. And that would be the off-bow principle. So we have the Pauli exclusion principle. The next thing we have to look at is off-bow. I don't think you need to know these names. Off-bow just says fill the lowest energy first. Fill lowest energy first. So that's it. However, when we go, let's see. So we go lithium, beryllium. What comes next? Boron. Where does the 5th electron go?
2, 1, 1.
Yeah, it could go, actually, it could go into any of these. The 211, the 210, and the 21 -1 are what we call degenerate. Degenerate means that they have the same energy. And so these are energetically degenerate orbitals, meaning that it doesn't matter, I can pick one. But, out of convenience, which one will you pick?
Yeah.
Yeah, just pick the 211. And should I put it spin up or spin down? Does it matter? It doesn't matter, but out of convenience, we're going to do spin up. And so how would you label this electron? What are the 4 quantum numbers that define that electron?
211 plus 1.
Yeah. Okay, now when I go to carbon, I have one more electron. Now these are all energetically degenerate, so it depends. Does this electron want to hang out with another electron, or would the electron rather have an orbital all to itself? What do you think? Will the electron prefer to have the orbital all to itself or double up? In other words, would you want a roommate, or do you want to have the room all to yourself? Probably all to yourself. Well, you know what? The electron wants the same thing. It wants to have the room all to itself if it doesn't cost any energy. Here, if I pair it, then there's a little bit of repulsion. The little bit of repulsion results from the electron's charge. This is negative, this is negative. 2 negative charges repel each other. And so if it doesn't cost energy, we're going to do this. You know what they call that? They call that Hund's rule. So Hund's rule says that if you have a set of degenerate orbitals, you fill them one at a time so that everybody can have their own orbital until you can't. And not only do you fill it one at a time, you fill it one at a time with parallel spin. Having the spins parallel like this is better than having them anti-parallel in these energetically degenerate orbitals. And so the first one spin up, then the second one's got to be spin up. If the first one spin down, then the second one's got to be spin down. They got to have parallel spin versus anti-parallel spin. And so carbon's going to fill like this. And then we move on to nitrogen. Nitrogen wants the orbital, this electron wants the orbital all to itself. So it's going to go like that. And so this would be nitrogen. And then we go to oxygen. Well, oxygen adds another electron, but that other electron can't have an orbital all to itself. Do you see? It's got to pair up. It could have an orbital all to itself, but it'd have to jump to the next energy level. Jumping to the next energy level is not favorable. It's going to cost you energy. And so what's got to happen here is for oxygen, it's got to pair. It could pair in any of these 3 because they only differ in orientation. And so we'll just pair the first one. So this will be oxygen. And then chlorine, it's got a pair. This. And then we get to neon. Neon takes the last remaining space. And so when we're at this neon, the second shell's filled, the first shell's filled. So the first shell's filled, the second shell's filled. This is neon. We call it the neon configuration. The first shell's filled, we call that the helium configuration. Here. Let's go to the third shell. The third shell is going to start off with sodium. So sodium is going to have, helium has 2 electrons. Neon's going to have a total of 10 electrons. Here. So when we go to sodium, which orbital are we going to? We're going to pick the lowest energy. That's off-bow. Off-bow says fill the 3s before the 3p because the 3s is lower in energy. And then we will put an electron here. That's sodium. And then when we go to magnesium, off-bow says fill the lowest energy first, so it can't get its own, but it's got to pair up. This is poly. Poly says it's going to spin down. So that's magnesium. And then what do we have? Aluminum is going to fill one of these here. And then Hund's rule says, well, these are all the same energy, so if we're going to put another one, might as well give it its own room. So Hund says fill singly with parallel spin. So this would be silicon. And then phosphorus would be another electron. And then after phosphorus comes sulfur. We got a pair. Spin down. followed by chlorine, followed by argon. So when we get to argon, we filled the third shell. So we call this argon. Argon has a total of 18 electrons. We count them up, 2 plus, in the second shell we have 8. In the third shell we have 8. So 18 electrons total. And so for argon, the first, second, and third shell are filled, etc.
Did they always fill the shells with the spin first?
What's that?
The electron with the spin up first?
No, it doesn't matter. You can go spin down if you want to be, rebellious. You can go spin down, but most people do spin up. It doesn't matter because if you do your spin down and everybody else does spin up, nobody's going to complain about that.
I was just wondering if there was like a rule.
No, there's no rule. Because when you're in space, is there a right side up or wrong side up if you're in space? Well, I guess if there's gravity, then you can be right side up or wrong side up. But if there's no gravity, is there really an up or down? No. And so you could have atoms out in space, it's no big deal. So up and down is just relative to what you define as what's up and down. So your up might be somebody else's down. Like they say, if you drill a hole through here, you might end up in China, but they're all upside down in China. Something like that.
Let's try it.
We don't need to know the names, right? We just need to know the principles.
You don't need to know the names, I think. Yeah, I don't think you need to know them. In Chem 1A, they might make you learn the names. You just need to know how you fill them. In Chem 1A, you may be asked, what is Hund's rule or something like that. That kind of stuff.
Yeah, that's a taste. It's the thing where they like.
Is this what they're talking about with quantum computing? They use the qubit and it's like
No, it's in the box.
the electron spins through
You don't know
these bits.
Yeah.
Yeah. Isn't there a 50%
That, and then they're talking about
right?
entanglement, quantum entanglement, and this kind of stuff to keep track of data and information. Yeah.
It's like about like the
You have spin states you can have in quantum, plus 1/2.
So are those
Did it make a
are
sound?
those electrons that
Or
are
like, yeah,
that are
exactly.
entangled?
That shit is
Are they
so.
ions? Is that
Photons. The photons are like a particle of light. Light is weird. I don't think I skipped this. See if they talk. We didn't really talk much about photons.
What's gonna be called?
The photons are kind of like a little particle of light. So an X-ray photon has more punch than a red photon. And the photons aren't actually particles. Photons are light, but they have particle-like properties. But we'll talk more about this later. What I wanted to do now is I forgot to put a stoichiometry problem on the test. I wanted to put a stoichiometry problem, but we'll have to get it. You're glad I didn't.
I'm just kidding.
No, I feel bad if you studied for stoichiometry and there was no stoichiometry problem on the test, and you just wasted some time. So we'll have a little thing where we can do some stoichiometry here. Maybe since this will be a quiz, in-class quiz, we'll pick a little harder problem for that.
You just gotta believe
You're
me.
giving us a quiz right after the midterm.
What? That's so. Yes.
Because Because it has to do with color is gender. So
It shouldn't be difficult.
and since men get
You know he's not gonna do that, he's gonna challenge it. Well, it depends. Do you want it, closed book, or do you want open book? Do you wanna work with other people, or do you wanna work alone?
with other people.
You wanna work with other people? Yeah. All right, then it's gonna be a little bit hard. Well, it's not gonna be so hard. It's not gonna be so hard because, you might have seen it before.
Yeah, I'm really stoic because I was touching me. Bro, you put your feet there. Okay, well, you
Cash the note first.
I know you got a bunch of practice check marks.
Okay. Let's do, can you do number 77?
But I like to see it close.
You have glasses because you don't need them.
Isn't this on the homework?
Yes.
Oh, wait, no.
This is chapter 10 though.
It looks so similar to,
This should look similar, right?
yeah. Yeah, I feel like we did this.
Yeah, we did this in class, but this is a very common stoichiometry problem, so it doesn't hurt to do it again. Can you do it again without looking at what we did in class? Let's see, yeah. And then if you can't, then look at what we did in class.